Okay, so we're looking in the section of sequences, and sequences are a list of items. Okay, so they are always separated by a comma. All right, so remember, a sequence is a list. It is a list of things. You can just continue to list those items as such. Okay, so we would write a sequence as follows. So here's some examples. Okay, so I'll have a sequence AN, and AN, N equals 1 to infinity. Looks like the square root of n. So that's how, so we're going to have 1, square root of 2, square root of 3, 2, square root of 5, square root of 6, square root of 7, square root of 8, 3, exactly that. Okay, and then the nth term would be the square root of n. All right, so I could write AN is the square root of n. All right, sequence BN, n equals 1 to infinity, and this is the sequence 1, negative 1/2, 1/4, negative 1/8, 1/16, negative 1/32. So we figure out that the nth term in the sequence, well, it alternates, so it definitely multiplies by -1. Now I need to see, is the first term going to work? So it's -1, but -1 to the first power would be negative. So it has to be -1 to the n minus 1. Now that works. And then it is divided by 2 to the n minus 1. So now we know Bn is -1 to the n minus 1 over 2 to the n minus 1. Okay, Cn.
Excuse me, Dr. Lott.
Yes.
Will the homework date be changed for this one? Because it was supposed to be due yesterday, but we
I'll
didn't
change
cover
it.
it.
No problem.
Okay.
Thank you. I will change it. Cn, and Cn is 0, 1/2, 2/3, 3/4, 4/5. And can anybody give me an idea of what they think the nth term is going to look like in this sequence? And again, n starts at 1 and goes to infinity. Now, what do you notice about those numbers, those fractions?
Would it be like n minus 1 over n?
That's exactly right. Okay, so you guys are going to have to figure these out. So Cn, you can see that if n is 1, n is 2, n is 3, n is 4, n is 5, so I have n, and then above it looks like the number n minus 1. Okay, so this is the notation we're going to use. The notation will be AN. Will be n equals 1 to infinity, and that will be A1, A2, A3. Okay, and it will continue. AN, and then it will continue. Okay, so just so you know, This is the notation we are going to use. Okay. Now, what did we talk about? Convergence and divergence of sequences. Okay, well, we want to know whether or not a sequence goes to a particular number. All right, so can we see that it's getting close to something? Okay, so if we looked at that first sequence, that was first sequence AN that I did, n equals 1 to infinity, that looked like 1, 2, 3, 4. If you keep going, it just goes toward infinity. Okay, so this sequence diverges. Okay, because as I look at what happens as n goes to infinity, a sub n goes to infinity, because that's what it is. Okay, so let's look at this sequence b sub n. Now b sub n, I want to try to draw for you. So here's b sub n. And b sub n is the sequence 1/2 to the n minus 1. And then n goes from 1 to infinity. All right, so we already know this sequence is 1, 1/2, 1/4, 1/8. We already know that's what the sequence looks like. 1/2 to the n minus 1. Now let's say I was to draw this sequence on a number line. And here is 0, here is 1, here is 2, and then of course somewhere down the line here is -1 or whatever. Okay, so I can see that my first number in the sequence A1, here's A1 is 1, and A2 is 1/2, and A3 is 1/4, and A4 is 1/8, and A5 is 1/16. And I can see that they're kind of getting all scrunched up together. All right. Oh, that was supposed to say A5, not A16. All right. So I can see if I look at like this sequence, it says this sequence basically looks to me like it's trying to go to what?
To 0?
Yes. Okay, so this sequence is trying to go to 0. And actually, that's what it is. All right, so I can say this sequence actually converges to 0. All right, so here's a definition. The sequence A sub n converges to the number L if for every epsilon there corresponds an integer n and n is also greater than 0, such that whenever little n is bigger than capital N, then the difference or the absolute value between a sub n minus L is less than epsilon. Okay, so it gets very, very, very small. If no such limit exists, then a sub n diverges. All right, so now this right here, this section is going to take you all the way back to the beginning of Calculus 1, where you are computing limits. Okay, so to calculate the limit of a sequence, we compute the limit as n approaches infinity of a sub n equals L. If you can't get an L, then you know that the limit doesn't exist. All right, so here's some examples. Okay, so the first one, a sub n equal to 1 over n. Actually, yeah, I have minus 1 over n. Yeah, 1 to infinity. All right, so what does that sequence look like? Looks like minus 1, minus a half, minus a third, minus a fourth, etc. Okay, so then I'll compute the limit as n approaches infinity of minus 1 over n. But then I can pull the negative out and get the limit as n approaches infinity of just 1 over n. Now, this is the most fundamental limit ever. Okay, so this is one major limit that you need to know. And that limit is 0. So therefore, this is just minus 1 times 0. And so we just get 0. Okay. I'm going to write that just a wee bit different. This is equal to 1 times 0, which is 0. Okay. All right. And the next one, b sub n equal to n minus 1 over n equals 1 to infinity. We already know what that looked like. That was 0, 1 half, 2/3. We just did it. I'm not writing it out again. Okay, so that is the limit as n approaches infinity of n minus 1 over n. Now, if you don't remember how to do these limits, okay, this one I can just break up very easily. Okay, so as I break this up, this is the limit as n approaches infinity. I can break this up. N over n is 1 minus 1 over n. Okay. Okay. All righty. So we had limit rules. I hope you guys remember these. Okay, so these are the same limit rules from Calc 1. Okay, so let AN and BN be sequences. So I have two sequences, all right, of real numbers. And let A and B also be real numbers. I'll just write there an element of R. That's nice and simple. And we're going to assume the limit as n approaches infinity of AN is A, and the limit as n approaches infinity of Bn is B. Okay. Then we're going to have these following rules. The sum rule that if I take the limit as n approaches infinity of the sequence AN plus BN, okay, then I'm just going to get A plus B. I can just add their limits together. All right, the difference rule, not root, rule, says the limit as n approaches infinity of AN minus BN is just A minus B. That's simple. Those two are the easiest. Okay, constant multiple rule. We've already done that. We multiplied by -1. We did that one already. Okay, so the constant multiple rule says, let's let K be a real number. All right, then the limit as n approaches infinity of K times a sequence is the same as taking K and multiplying by the limit of the sequence. For product rule, okay, so if the product of two sequences, so the limit as n approaches infinity, if I have AN, a sequence times another sequence BN, I'm just going to get A times B. So I'm just going to get the limits, the product of their limits. And then the quotient rule, and that is the limit as n approaches infinity of AN over BN. That's going to equal A over B, provided B does not equal 0. Okay, so we already know that the limit as n approaches infinity of 1 over n is 0. So therefore the limit as n approaches infinity of 1 over n squared is the same as the limit as n approaches infinity of the sequence 1 over n times 1 over n. I know 1 over n goes to 0 and 1 over n goes to 0, so that's 0. In fact, if n is in the denominator, at any power, that limit is always 0, as long as p is positive. So it's in the denominator. All right, Now, some sequences don't have limits. So that's easy. So limit, here's an example real quick. Let's let an be 2n minus 3 over 4 minus 5n. Okay, so I would get the limit. Can anybody tell me what the limit of that sequence is just by looking at it? Can anybody tell me what the limit of that sequence is? Any idea? Okay. Let me show you how to do it. The easiest thing is to divide by the highest power of n. So I get the limit as n approaches infinity, 2n divided by n minus 3 divided by n all over 4 divided by n minus 5n divided by n. Okay, so that's the limit as n approaches infinity. So 2n over n is just 2 minus 3 over n. And then I'm going to get 4 over n minus 5. Okay, so now it's easy to see what happens. As n goes to infinity, this term goes to 0, and this term goes to 0. So I just get 2 minus 0 divided by 0 minus 5. So this limit is -2/5. All right, I hope that's a refresher for you guys and you remember how to do limits. Okay, so now let's look at this limit. Here's a problem, example. I'm going to call this an, and an is the cosine of n pi over 2. Okay, so we can start off with when n is 1. I'll make a chart first. Why don't I do that? Let's make a quick chart. So this is n. N is 1, 2, 3, 4, 5, 6, 7. All right. So therefore we get n pi over 2 is just pi over 2 pi, 3 pi over 2, 2 pi, 5 pi over 2, 6 pi over 2. Oh, that's just 3 pi. And then 7 pi over 2. So now when I take the cosine of that, the cosine of pi over 2 is 0. And then the cosine of pi is -1. The cosine of 3 pi over 2 is 0. Cosine of 2 pi is 1. Cosine of 5 pi over 2 is 0. Cosine of 3 pi is -1. Cosine of 7 pi over 2 is 0. So if I were to draw this out, I would get something that looks like this. It would be 0 here, then it would be 1. I'm sorry, it goes -1 first. It would be -1, then it would be 0, then it would be 1. Then it would be 0, then it would be -1, then it would be 0, then it would be 1. And so I'll keep doing this. As you can see, as n goes to infinity, I'm not going to get a limit. Okay, so here, note that the limit as n approaches infinity of the cosine of n pi over 2 dne does not exist. You will see dne a lot. dne does not exist. Okay. Whoops. I don't know what I touched, but somehow I went to module. Okay. All righty. So therefore we can see some sequences don't have limits. Okay, but here's one that does. And this one is Bn is equal to -1 to the n minus 1 over n. All right. So let's draw a chart again. I think you guys may have found that helpful. I hope. Okay, so I don't think I need all that. All right, so n, we had 1, 2, 3, 4, 5, 6, 7, 8. That's good enough. All right, well, so when n is 1, I put 1 in there, I get 1 over 1, so I get 1. When n is 2, I get 2 minus 1 in the numerator. So -1 to the 1 is a negative. So this is going to give me -1/2. Then I'm going to get +1/3 and -1/4, and +1/5 and -1/6, and +1/7 and -1/8. Okay. So if I were to, I don't even really need to plot this when you can see what's happening, but I will. Okay. So as I plot these things going out to infinity, when n is 1, so here's, I think I made a mistake. I think I made a mistake. I did. I made a mistake and nobody caught it. Here's my mistake. All right. This starts at n equals 1. Here's n equals 1. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so at each value is where I'm plotting it. So when n equals 1 here, when n equals 1, I'm at 1. And when n equals 2, I'm at -1/2. And when n equals 3, I'm at 1/3. And when n equals 4, I'm at -1/4. And when n equals 5, I'm at 1/5. And when n equals 6, I'm at -1/6. And n equals 7, I'm at 1/7. And at n equals 8, I'm at -1/8. Well, as you can see, all of these numbers are trying to go to 0. Okay, even though they're alternating back and forth, their limit is still 0. Okay. So this sequence converges. So we get the limit as n approaches infinity of -1 to the n over n is equal to 0. Okay, now I'm going to give you some commonly occurring limits, and you may need these. In whatever you do, you may need them. So please take careful to look at these commonly occurring limits. Okay, I think I spelled occurring wrong. Does occurring have 2 R's or 1? Does anybody know? I'm going to put in another R.
I think it's
that. Okay, so the first one, we already squared it off. The limit as n approaches infinity of 1 over n is 0. That's the first one. Okay, here's the second one. The natural logarithm function does not grow as fast as the function x itself. Okay? So you get the limit as n approaches infinity of the natural log of n over n. That limit is also 0. Now you can use L'Hopital's rule to show that. And many of these you can use L'Hopital's rule. Okay, so now the limit, you can use L'Hopital's rule to show this one as n approaches infinity of any number to the 1 over n is equal to 1, as long as x is positive. Because I can't take the log of a negative number. So now I know that limit, and we will use that. Number 4, the limit as n goes to infinity. So this is one of those things where I say you go home and you make sure you know it and you learn it and it stays in your head. That's this list right here. Okay, this is not a list that you have to go to refer to. You need to know this. Of 1 plus x over n to the nth power is e to the x. Okay, so that's another limit that you need to know. Number 5, the limit as n goes to infinity of the nth root of n otherwise known as n to the 1 over n is equal to 1. Okay, another way of writing that is the limit as n goes to infinity of n to the 1 over n. That limit is 1. Okay, number 6, the limit as n goes to infinity of x to the n is equal to 0 if the absolute value of x is less than 1. And number 7, the limit as n approaches infinity of x to the n over n factorial is also 0. Okay, so these 7 limits are common limits that you're going to see as part of other functions. And so you're going to need to use those. Okay, so I'll give you some quick examples. Okay, so 1, AN is the natural log of n squared over n. The question is, does this sequence converge or diverge? Does this sequence converge or diverge? Anybody have an idea of how to take care of this problem? I'm going to simplify it first. How about I do that? How about I use the log property, bring the 2 down and make that the natural log of n over n. Does that look any better? I now know that if I take the limit as n goes to infinity, this just becomes 2 times 0 equals 0. Because remember, we already said that this piece, the natural log of n over n, goes to 0. Okay, I'm going to pause. All righty, so where were we? Right here. Okay. Some of these are really clever. You have to be able to maneuver them. 2, Bn is equal to the nth root of n squared. You will see that kind of thing a lot. Okay, so you're going to need to rewrite that as the nth root of n squared. So now what do you know about the nth root of n? We know the nth root of n goes to 1. So if we take the limit as n goes to infinity, this looks like 1 squared. So that's just 1. All right, here's another one, another little tricky one. Cn, it looks like n minus 2 over n to the nth power. So rewrite it as 1 minus 2 over n to the nth power. Okay, we saw that one a minute ago. That looked like e to the x. So this one, the limit as n goes to infinity, this one goes to e to the negative 2. So some of these are tricky. Okay. Oh God, how much more do I have? Oh my God. There's no way I'm going to do all that. I have like 5 pages of notes. I think I'm going to send y'all these notes and let y'all look at the rest of this. I'm going to do this because there's no way I can do all that. The sandwich theorem. Okay. All right, so the sandwich theorem is pretty simple. It basically says if I can sandwich whatever limit I'm trying to look at between 2 functions and they have the same limit, then it has to be the same. Okay, so let's let an, bn, and cn. So now I have these 3 sequences of real numbers. Okay, if AN is less than or equal to BN is less than or equal to CN for all N bigger than or equal to some N. So you just have to find this N large. It's a very big number. Okay, and the limit as N approaches infinity of A sub N is the same as L is the same as the limit as N approaches infinity of C sub N. So the biggest one and the smallest one have the same limit. Then that implies the one scrunched up in between also has the same limit. So then that implies that the limit as N approaches infinity of B sub N also. Okay, and this is called the sandwich theorem. So here's an example. The limit N approaches infinity
Oh, God damn.
cosine
Nothing.
N over N.
What? No, it's just, what? No, because I didn't use anything.
Somebody needs to mute.
Yeah.
Okay. So -1 is less than or equal to the cosine of N. And that's less than or equal to 1. Alrighty, we got 1 minute, just enough time for me to finish this. So -1 over N is less than or equal to the cosine of N over N is less than or equal to 1 over N. So now the limit as N approaches infinity of -1 over N, we already did that. That was 0. And the limit as N approaches infinity of 1 over N, we already know that. That's 0. So since this cosine function is sandwiched in between, that means the limit as N approaches infinity of the cosine of N over N is also 0 by the sandwich theorem. Okay, everybody, I will see you tomorrow. I will fix that homework to make it not due today. All righty, thank you.
Professor,
Yes,
what sections will this next test cover?
that's what I'm getting ready to put that on the announcement.
Okay, thank you.
You're so welcome.
Dr. Love.
Hang on 1 second.